to the cloud. Yep, we are recording. Well, welcome to today's session. We have two participants from very far abroad, from Australia. And first is Meera. Please, on the screen. We're very happy to see you talk.
Okay, great. Yeah, thanks. It's a pleasure to give a talk, even if it's unusual circumstances. I think this is the first time I've given such a talk at 10 p.m. at night, so I apologize if I'm at all incoherent. I'll do my best. And please stop me if you have any questions as I go along. So what I'm going to talk about this evening, or today, this afternoon, is some recent work we've done on what I call the quantum behavior of a heavy impurity in a Bose gas or a Bose medium. So I probably don't need to introduce this too much to this audience, but let me just start with the general motivation of why we're interested in, or why you might study impurities in a Bose medium. It's a fairly fundamental problem in physics, occurs in many different scenarios. It's in some sense like a version of a quantum system plus environment problem. So it has been studied in various realizations in that context. So one example, for instance, is the so-called spin boson problem, where you have a spin or two-level system coupled to a bosonic bath. There's of course it crops up in solid state physics, where if you have electrons moving through an ionic lattice or a crystal, it becomes dressed by phonon excitations to form the traditional kind of polaron. So what I'm going to be looking at or discussing today is the one that we can readily realize in cold atomic gases. So basically thinking about the situation where, what about if the medium is a Bose-Einstein condensate, a BEC, which has been realized in many experiments, recent experiments. And in particular, we're sort of interested in what happens when you have an impurity atom, for instance, which is strongly interacting with the Bose-Einstein condensate, or with tunable interactions. So you can tune it all the way to strong interactions, strong short-range interactions, I should say. So that's the key point here. And so what I'm going to really talk about is, so what I'm going to be focusing on, so this is the outline of my talk, I'm going to be focused on the three-dimensional problem. So just 3D, not lower dimensions, although I think there are some interesting questions there as well. And what I'm going to start from is sort of build up the picture, start from thinking about what happens when you have, say, an impurity with n bosons, so looking at few body bound states, and all the way up to the many body limit. And what I want to kind of impress upon you, and what we've realized, is that actually the range of the interaction, or the range of the impurity boson interaction, is very crucial for how this so-called Bose polaron problem behaves. Okay, so what I'm going to do in this, what I'm going to simplify it a little bit further and say, okay, what if we take a situation where I have an infinitely heavy impurity? Although what I'm going to argue is actually many of the ideas are going to carry over to the case when you have a finite mass, or at least a heavy or reasonably heavy impurity. But I'm going to imagine I've got a very heavy, infinitely heavy impurity. I've fixed it in my gas, my Bose gas. Okay, and I'm going to assume I have a very weakly repulsive Bose gas, and I have tunable short-range interactions between my impurity and bosons. So I presume hopefully you can see my arrow in my cursor here.
Your pointer.
Okay. Oh yeah, a pointer. Yeah. I don't know if I can. Oh, well, okay. I can try and use the pointer, but maybe. Well, let's see. Try this. Let's see if I can advance the slide. Okay, so basically here's the sort of typical Hamiltonian you have, where you have like a Bose gas. This is the kinetic part, where I have a quadratic dispersion with a mass, a Bose mass. I have a short range. So this term here is describing the short range interaction between the bosons and this fixed impurity. Okay, so this this coupling G term can be related to an S wave scattering length. Okay, so in the usual manner, so where you can think of it as essentially a zero range, or at least a very short range interaction governed by this cutoff here, this high energy or high momentum cutoff here. And now this term is now we have a boson-boson repulsion, which is also some kind of short range repulsion that we're going to consider here, governed by some scattering length, boson-boson scattering length in this case. And so I'll come back to this in a moment. So the various ways one could maybe implement an effective interaction. But let's suppose now we just for the moment ignore, or at least assume we have an ideal Bose gas, ignore the boson-boson interactions. Okay, so we did remove that term as was done in recent papers. And now in this case, okay, it seems like it's an exactly solvable problem for this ideal Bose gas. Seems in fact it's even simpler than the fermionic equivalent, because what you just need to do is just solve for the single particle states in your potential, the boson impurity potential, and then you just put all the bosons into the lowest energy state. Okay, and so what you find, let's suppose you don't have a bound state, so you have a negative scattering length. You can work out what the polar energy is exactly, taking the right limits, and you find it's just like a mean field, kind of has this mean field form here, where you have this is a boson density and boson mass here. Now what you see there is we have a slight problem, because actually this is rather singular, because you can see that as soon as you can see that this will diverge once the scattering length diverges. So once a bound state appears in your problem. Because what ultimately happens then is that, once you have a bound state in your potential, your impurity boson potential, all the bosons just want to collapse into that bound state. And so now your energy diverges in that case. Okay, so this is already giving you a hint that the interactions are going to be very important, and the interactions between bosons are going to be very important for this problem, for creating something that's a non-singular, or occurring this singularity, if you like. So so then the question then is, how do we think about how do we deal with these interactions? So let me take one step back and think about the situation where now I'm looking at the sort of a few body problem where I'm adding bosons one by one. So in the case, so once again, in the absence of interactions between bosons, and supposing I have now a bound state in my potential, so I have a positive scattering length between my impurity and bosons. And now, it's very simple. If I have n non-interacting bosons, I just all pile them into my bound state here, into my two-body bound state. Okay, so that's the energy of my polar. And so you can see already that this is obviously going to diverge as I take n to infinity in the thermodynamic limit. So now we ask the question, so what about the effect of boson-boson repulsion in this case? So non-zero scattering length AB. And so what you can do in this case, at least we looked at this, we can do exact calculations. So for very small n, we can solve it in various ways and various models. But if you want to go to larger n, we resort to quantum Monte Carlo in sort of variational quantum Monte Carlo in that case. Okay, but in principle, it's possible to do exact calculation. Sorry. And what you find, if you look over here, is that so here's a picture of the energy, and I've just divided it by the two-body binding energy here. So we're still at positive scattering length. So we always have a bound state. So we have the energy as a function of the number of bosons here in this case. And here I've just actually taken a very weak interaction. Relatively weak. This AB is like 100th times smaller than the S wave scattering length for the impurity boson interactions, and so you see that there's a very strong correction due to this interaction. So here, this dashed line here, this dashed gray line, is this ideal kind of non-interacting situation where you just very strong increase in the strongly going downwards as you add bosons. And you see it, this is markedly changed once we actually add an interaction, quite dramatically. Okay. And actually, what's even more interesting, actually, or what's perhaps crucial to bear in mind here is that now, even if you just look at this one here, so this one is what you can call the trimer, as in it's got two. What I mean by trimer is you have two bosons plus the impurity. So you have this. So that's my kind of trimer n plus 2+1 kind of state here, my trimer. What you find actually, as we've plotted down here, is that this state here. Okay, so not only is it sort of strongly impacted by the repulsion, but actually there's even, I mean, if for a given repulsion here, or there's a critical, or even if you like, there's a critical kind of ratio at which the trimer is no longer even bound. Okay, so you only have the only one boson combined at this point. So in other words, and it's very you can kind of argue it in a sort of hand wavy sense. The way you can think of it is, let's suppose I'm imagining over here, if I imagine the energy it costs me or energy of adding another boson to my my dimer system. So I have my impurity plus a boson already in there, and then I decide to add a second boson. Yeah. Yes. Oops. Is there a question, or is that?
Yeah, we hear some question, but it's almost hard to hear. Is anybody raise the hand if somebody wants to ask question? I will see your hand.
Ils disent quel est leur seul pièce justificatif demandé, c'est aucune pièce de figure dans cette liste, vous n'avez rien à transmettre, mais je vois pas de liste, donc juste que j'ai rien à transmettre.
Pardon me, I don't see even who is asking.
T'as pas des trucs de, est-ce que t'as des trucs de, comment ça s'appelle, d'assurance, non?
No, in English, please. Xavier.
Oui, cette liste dont il parle.
D'accord, ok.
Xavier.
Il y a écrit sur une pièce de figure dans cette liste. Et là, je vois pas de liste.
Okay.
Okay, I'll he doesn't know. Wait, I'll switch off his. Wait, подожди, wait, I will. Let me check.
No, but this is very simple. So how do you ensure that because it is repulsive bound state?
Bah écoute, ouais.
Sorry, I had a question. How do I ensure that what?
The Bose interaction is repulsive.
How do you ensure that the Bose repulsion, the Bose interaction?
Oh, right. Yes. Sorry. No, that's a good. Yes. So what we assumed here. So I skipped the details. So what these dots calculate here for this particular case is the taking hardcore boson-boson interactions. So the hard sphere interactions. Yeah. In this is a quantum Monte Carlo calculation here. Yeah, but what we find actually is we can include the repulsion in a couple of other ways. We even, for this this n equals 2, this trimer situation, we also, we even took a situation where the effective boson-boson interaction was actually attractive. So in other words, we took an actual zero-range interaction, but it still had a, a positive scattering length. So of course, in that case, it's not truly repulsive. It's actually only, I mean, there is the kind of state that we're calculating here is now a metastable state. There's actually dimers that are much more deeply bound. But we found we could also, in that case, even reproduce this kind of behavior. Okay. But yeah, so there are various ways in which we could include repulsion, but of course, certainly the most straightforward way, which is definitely a repulsive interaction, is when we had like hard sphere interactions. Yeah. Okay. But yes, no, it's, yeah. So what we okay, so I was saying that in this case, you find that you can
I see a hand from Nikolai. Nikolai, you want to ask something?
Yeah, I have a question because we have a paper which says the opposite. Because when you say that there is no bound state, you have to be very careful that the binding energy can be exponentially tiny.
Oh,
So
yes, yes, definitely, yes.
So
But I
essentially,
believe-
our paper is saying that no way. So even if you have hardcore bosons, the moment you have some bound state in the two-particle channel, you not only you have trimers, 5 particles, it's actually always infinite number of bosons which will bind to a generic potential. You never
Yes,
have any
yes.
threshold for any finite n.
Yes, yes, no, yeah,
But
no,
to
I,
get-
I,
but-
I,
but to-
I'm aware of
Yeah,
your
but to
paper,
get
yes.
this solution, you have to run at extremely low temperature. So for example, when you say it's Monte Carlo, I would like to understand whether Monte Carlo was running, for example, with inverse temperature, measured in units of 10 to 5.
Right.
Because if you don't do it, you will not see the bound state because it's simply outside of your system size or the temperature is too high.
Yes, yes, no, yes, no, I think, yeah, I'm aware of your paper, and I think basically I agree, but it depends on the region in which you're looking at. So I totally agree that within a certain range of scattering lengths.
No. Just our statement was without any range of scattering length. If in the two-particle channel, which means one boson, one impurity, if you have a bound state, then it doesn't matter how many bosons you have and how they interact, you always bind an infinite number of them. That's the statement.
I think you had to assume that the scattering length was sufficiently large, if I remember correctly.
No. Just what I'm saying.
No,
No, that's exactly what I'm saying. Just well, you don't. That's what we are not assuming. Our result is the moment you have a bound state in the two-particle channel, which means
Yes.
one boson, one impurity. If you have a bound state, doesn't matter shallow or deep. At this point, no matter how bosons interact, including hardcore, you always bind an infinite number.
Yes, I mean, but we've done other calculations which show that there is a critical. Actually, we had a paper around the same time. Yours came out, but it was.
Yeah.
I mean, we're looking at a different model. Yeah, we've shown that there is always a critical interaction. Oh, okay. If you fix the boson scattering length, and then you lower, if you lower the take the impurity boson scattering length to be small enough, then you always find that there's an unbinding transition.
Mhm.
So I totally agree that there's away from that point, you have to be very, you can bind an infinite, it looks like you can bind an infinite number of particles and they become exponentially weakly bound or very, very weakly bound. But there is a critical scattering length at which all of these disappear.
Yeah. Oh, you mean, and this A is still positive?
A is still positive, yes.
Yeah, that's.
Can I just say, I don't understand, how can you have, if you just have a two-body bound state, how can you then bind an infinite number of bosons? It's maybe to Prokofiev.
Because the state.
Because I mean, the repulsion between the bosons you scale as n squared. So
No. Because once you repulsive interactions between bosons will make the state more shallow, so they're staying far away from each other.
okay, so they compensate by going further away from each other.
Mhm.
Okay.
Yeah. So another way of, because you can also think of it as if you go to closer and closer to unitarity, for instance, and you're also making the dimer larger and larger, you can, then the boson interaction becomes less and less relevant as well. If you see, so then also in that case, you can start, you approach this kind of expression here as well, as you go, once this dimer becomes very, very weakly bound. Yeah. Okay. But I mean, it's true. Yeah. Okay. I didn't include so we have a whole other paper on this point, but I didn't include the universal expressions. But what I was trying to at least do in a hand wavy sense, but you're right.
You have more hands. They won't let you easy. So go ahead. But it's good. Wow.
What I was trying to argue. Yes. I'll just say we have done
on one hand, I want to second Nikolai, and I want to emphasize, so on the other hand, I can maybe partially agree with Meera that there probably can be a situation when the number is finite. But what is important in terms of our paper, that in a very counterintuitive limit, when the trapping potential vanishes while you keep repulsion finite, you trap an infinite number of bosons. So let us put aside the situation when there is a transition. Our point is that the transition is absent in the very counterintuitive limit when the scattering length is finite, while the trap is arbitrarily shallow. And I'm just reminding that the question is very robust because we deal with the tail of the Gross-Pitaevsky description, which becomes progressively controlled. So it's, if you will, it's a mathematical theorem rather than the result of simulations. Sorry for interrupting.
No, yes, I did. We did read your paper. It was interesting, and I think basically, it's okay. So we had a paper around the same time, I think, which we dealt with it we dealt with it a different problem in a different way, but I think we basically come to very similar ideas, similar conclusions.
That's a purple line.
And that's this. So this is this. So that's from that paper, this purple line here. But So anyway, let me. Okay, so you're absolutely right. You have to be careful. But what I wanted to say is that you can certainly at least argue, and this is backed up with very careful calculations, not just quantum Monte Carlo, but also other calculations we've done in many different ways, and they all say several different models, with two-channel model, with where cutoff models, and we find basically the same behavior. So we find the same behavior. It appears to be universal. So what we find is there is a critical interaction. So I think this is still consistent with what you were saying, Boris, because it's not necessarily now a very shallow bound. As it's not a shallow potential necessarily. So we have this counterintuitive situation where, as you make the potential deeper, you're actually less able to bind particles. So, and the reason you can kind of understand this is that if I consider now I'm adding a boson to my, adding my second boson, as I've written down here. Whoops. So that you say, okay, like I get my binding energy here, or my, the traction here, this minus EB, and then I pay this penalty of this interaction with the other boson. So that's the AB, and then I have I've divided it by A cubed here, because that's essentially the volume over which it interacts in this bound state. And the key thing here is that you see that this is going to grow faster as I take this A to be smaller. So even though they're both increasing, this bound state, the binding energy here, and this here as well, this increases faster. So eventually this repulsion will win. And so there will be a critical, as I lower A, there will be a critical scattering length, roughly proportional to, scaling with AB, at which I lose my trimer state. And what we find, at least, okay, so for the quantum Monte Carlo calculations, we find it's a factor of 10 between the two. Like I said, we've also looked at other models, like even we looked at this situation, as I was mentioning before, where we have actually zero range interactions between our bosons. So like I said, it's actually attractive interactions, but they still have the same boson scattering length. And then we get a similar result. We lose the trimer, except now it's maybe like, it's 20, this factor is 20 instead of 10. So this factor will depend on the precise model that you use, but point remains that there is a critical scattering length at which you lose your trimer. Okay. Right. So so it sort of fits in with this counterintuitive idea that, funnily enough, as you make it deeper, you make it less able to bind particles, and that's because of the repulsion. So I think that's consistent. Is there any other questions about this, or shall I? Okay.
The way how it sounds, yes, we have clear contradiction, because we say that A star is infinite. It cannot be finite. In our case, it's a theorem. So I think, yes, we are in contradiction with each other.
Well, I think, okay, we can discuss, but I think we're talking about probably different regimes, and yeah, I agree with you, close to unitarity. Okay, right. So what this means, if we believe, which we've shown with many calculations, that since you have a critical scattering length at which you lose your higher order bound states. You only have the dimer state. What you find is actually, because once you've lost the trimer state at that point, all of the higher order bound states unbind at that point. So if you like, it's very much, it's what you can show is actually equivalent to like a unitarity point for the case of a dimer impurity. So in the same way that if you had your impurity, bare impurity, and now the scatter, you now suddenly, as soon as you can form a bound state, as two-body bound state, you can form n infinite number of bound states close to unitarity. So that's consistent with what Boris and Nikolai were saying. So that in that case, what you find, there's another end where now once you lose your trimer bound state, all of them get lost at the same time. So now you only have the dimer left after this point, after this A star point. And what we find, and what I was showing here is actually, okay, so this is what I've plotted here. So this is the energy versus this, okay, A star over A. So at 1 here, that's the scattering length at which they all unbind. Here are the quantum Monte Carlo points here, that plus, and these lines here are calculations from other models, like I was mentioning. So other calculations, not this quantum Monte Carlo, where we fixed the sort of same A star here. So we fixed, so even though the different underlying models, we have different ways in which we get the A star. If we fix them to be the same point here, if we plot them in this way, they all have essentially the same kind of behavior here. And the same thing even occurs, this is for the case of the tetramer n equals 3. It also disappears at this point and has the same kind of similar kind of slope. So we're seeing, at least for the small n's, that there's this universal or sort of behavior close to this A star point. And what this also means is that what you can also conclude from this is that the ground state energy must be bounded from below for any boson number n. Okay, so how do I conclude that from this fact that I have this A star? It's basically using the fact that we know that the energy has to be monotonically decreasing as I as I go towards A star. Yeah. Okay, so notice, okay, so here, the way I plotted it here is, it's not so obvious because I've scaled it by EB here. So the EB is also increasing. So actually this energy overall is decreasing as I go towards A star. Okay, so, and we know that this energy is bounded by whatever this value of this energy is at this point here. Okay, so that's really just using the fact that we must have this requirement here. This derivative must be greater than 0. So it's another statement that the tan contact has to be positive. So we know that if you have this point where, when we know that this has to be, you just have the dimer state, everything's unbound, that already bounds what the energy should be for all the other bound states to the other side of that point. Okay. All right, so these are 3 kind of consequences of having this particular A star. Okay. All right. Okay. So any questions about that before I move on to the many-body limit? So I think so basically what we've learned, what I want to stress about the few-body case is that the strong effect of interactions and how they repulsion between bosons, how they can really often be counterintuitive, as we've been discussing. How strangely enough, as you increase the attraction, you actually lose the bound states. Okay, so there's sort of a very strong effect. So now, if we go now to think about what about in the many-body case, so this is all essentially in the 0 density limit, what I was showing before. So a popular approach in that case is to treat the BEC as a classical field. Okay, so whether it's Gross-Petevsky or a coherent state, and there are situations, okay, so many situations, of course, where that's valid, but I want to point out, okay, so of course, one thing it kind of ignores is it ignores, if you like, the quantum granular nature of the gas. And what I want to emphasize is that actually this is crucial for a short range impurity potential. So in the sense that what this kind of classical kind of continuous sort of field cannot describe is a situation where I have a very short range potential such that the range of my impurity boson potential is of order or even less than the typical size of my, the scattering length here, the size, if you like, the size of my, if you think of them as hard spheres, say the size of the spheres of the boson-boson interactions. And so maybe another way to put it, actually, is the reference to also to Boris Nikolai's paper here. Another way to think about it is in this classical field approach actually has two conditions to be valid. And so the one hand, you need this dilute gas condition. Okay, so what you usually assume if you write down a Gross-Pitayevsky equation, you require weak interactions. Okay, and you require that everywhere in your kind of system. So this is, okay, so here this NL is just what I've denoted as my local density at the impurity. So I require the local density at my impurity times this A B cubed to be much smaller than 1. Okay, so that's on the one hand, that's one condition. The other one is actually that you require the number of bosons actually, if you want to talk about, a classical field of bosons, you also require the number of bosons interacting with this impurity at that point to be larger than 1. So that means, on the other hand, that the density of bosons times this effective volume of the impurity potential, so that's given by the range R cubed, you also require that to be greater than 1. So based on that argument, what you find is actually this classical field approach is only really valid if R naught is much greater than AB here. Okay, and I think this was also, this was also pointed out in at least for the zero density limit by Nikolai and Boris as well in this paper. So okay, so basically we need to be careful once you have, whoops, sorry, go back here. If you have a short range interaction.
It's hard, at least for me, I'm not in this kind of exactly field. This condition of applicability, is it kind of discussed, or this because to me it's counterintuitive. If you have classical field, you have classical field. Why, if you kind of look and overlap with a kind of local potential of an impurity with a short range, okay, with you can't with long range or whatever, with this broader potential you can, is it kind of obtained from some first principles, or it's just the intuition and suggestion? I don't understand how these pictures were kind of, is it a result or it's a hypothesis?
I mean, like, how do I make
with this one, what I mean.
Okay, I would say, okay, so I would say that this is so I would say it's been a big under discussion for quite a while whether these kind of approaches work. I would say based on our results, we're finding that this kind of classical field doesn't work, and this is essentially the picture that this is a sort of simple picture as to why it doesn't, what's going on.
So it's a posteriori explanation, or that something doesn't work.
Yes.
Okay.
Yeah.
Sorry, can I interfere again?
Well.
Sure.
Well, first, the classical field picture always works.
Yeah, that's what I was. You try. But whether it gives you correct result is another story, right?
Yes. Well, let me answer your questions. First, the classical field approach always works far away from the trap, where density is low by definition, because the density decays to 0. Whether classical field works within the trap is irrelevant, because at this point you have to do two things. If it's true within the trap, okay, do it within the trap, but that's too restrictive because traps can be narrow and deep, and interaction between bosons can be strong. For this, you just do a numerical solution by Monte Carlo, and that's what we did. And we always find that you trap infinite number of particles. no matter how strongly bosons are interacting or how deep is the potential or how narrow it is. Yes, classical field doesn't work on the size of the trap in some cases. That's when you have to do numerics. By Monte Carlo, exponentially large, exponentially blah, blah, blah. So you have to be very careful at the level of 4 to 5 digits to see the bound state. But away from the trap, in the far field, far away from the trap, where the density profile starts decaying to 0, that's when the classical field always works. And that's where our theorem is coming from, because it's universally correct, because density drops to 0 by definition in the tail of the localized distribution.
Yes, yes. I don't. Yeah, no, sure. I don't think I'm arguing about that. But I think what the problem is that a lot of this classical field approach has also been applied at the point of the impurity potential. That's where things start to fall apart. Like especially
that's where you do quantum Monte Carlo for sure, just to establish that short range is done properly exactly. And then you go to the field, to the tail where the classical field approach works. Yes,
well, I mean,
for strong interactions, you do numerics.
Right. It depends on what you're trying to do, right? So I know your calculation was a zero density calculation.
Yeah, that's what we say. The zero density means you trap infinite number of particles.
So right. So I'm looking at a situation where you
find Bose gas. I agree. For finite Bose gas, there is a threshold, because binding energy is less than the chemical potential in the gas already makes no sense. Yeah.
Right. So yeah. So I mean, I don't think we disagree with each other. I'm just pointing out that I guess it's a question of what kind of question are you trying to answer here, and yeah. So I think we agree at the few-body level, and I agree, of course, if you go away from the impurity, the classical field approach works, whether it's finite density or whether it's zero density limit. But if we're now trying to understand what happens when you when you suddenly switch on a potential, like how does the energy change? When you've got a gas, finite density gas already there, then what we're finding. Okay, so I mentioned this quantum blockade kind of picture. I think this is a very useful physical picture in which to understand it, because then it turns out you can do relatively simple numerics to actually understand what's happening, rather than just
Geo was first, then Vadim. Geo, go.
I'm sorry if I'm delaying you too much, Geo. Just something I don't understand. Maybe you can. So I don't understand this statement that the classical field doesn't work. Maybe, I mean, in a sense, maybe you can clarify this to me, because what's different from this situation and then just a BEC with a short range interaction?
Sorry, we didn't hear you. You don't understand what it means. Doesn't work or work. No, it was faded. Doesn't work or work.
I don't understand this condition NL arc 0 cubed larger than 1. Because it seems to be, I mean, can I just finish the question, Michael? Because when you do pseudopotential calculation for a BEC, you get this Li Huang Yang and all this. It's very well established calculations where you don't worry about the effective range. So what's different in this situation here? I guess I'm missing that.
Okay, right. So sure. So I guess that the difference is that okay, so I'm talking really about if you want to apply it for any kind of impurity boson interaction. So you're right, of course. If you go to weak interactions, weak coupling, small, weak impurity boson interactions, then sure, yeah, you can get away with your classical field approach gives the right energy. You can write down all sorts of, it's perturbation theory, right? I'm just saying that in general, though, if you start making a very strong interaction, then the classical field approach breaks down, as in that it doesn't give you the right polar energy.
Okay.
Yeah, close to unitarity. Yeah, and I think it's basically because it assumes that all the bosons can kind of pile in, or pile into the interaction. It doesn't really treat this kind of short range kind of strong repulsion, the short range repulsion between the bosons that's sort of in this picture here.
Yeah, just a quick question.
Sure.
I think I sort of understand your applicability conditions, but I didn't quite, probably missed it. What do you call the quantum blockade? What is the phenomenon?
Yeah, sorry. So yes, I possibly got lost in what I was saying. Yeah, so the quantum blockade is really all I'm saying here is that is the statement that so what's happening is what we're finding is that if a boson, as soon as one boson interacts with the impurity or short-range impurity potential, this already interferes with another boson interacting with this potential. So that's kind of what I'm calling this blockade effect. The fact that already if you have one boson, if you like, occupying the space where the impurity is, that already impedes the other bosons from interacting.
Right. Okay.
Yeah. All right. Okay, so I think, let me press on here. So, oops. All right. So so let me try and argue this a bit further and convince you all. So what I want you to consider is this general kind of state that I can write down. So this is in principle an infinite series of bosonic excitation. So here this state. Here, I'm imagining a very, very dilute Bose gas. So essentially, I can treat it to a good approximation as I can ignore the quantum depletion, and I have essentially all the bosons in the zero momentum state. And now I have this infinite series of bosonic excitations generated by interacting with the impurity potential. Okay, so one bosonic excitation, two, and so forth. Okay, all right. And these come with their various coefficients. And what you find actually, so what you can do if you write down such an equation, you can to a good approximation, you can even treat these as just bare bosonic interactions. I mean, in principle, they should be Bogoliubov excitations in your weakly interacting BC, but you can even just go ahead and think about them as just, I mean, that only affects this very small momenta. So we can even think of them as just bare bosons to a good approximation. So if you go ahead and okay, I'm not showing you all the details here. You have to trust me here. But if you actually go ahead and you try and you look at the structure of these equations for the polar energy. So you apply the Hamiltonian I showed you previously to this equation, and you solve for the energy. What you find actually is that I can write it in this very relatively simple form. Okay, so if my energy, here's my scattering length, the density, and I have this sum over k here. And of course now all the complexity now is buried in this g term here, this function g. And what this function g has is actually it encodes, it's a combination, okay, of involving these coefficients here. So it's essentially the difference between this kind of two boson coefficient and the single two boson excitation coefficient here, this alpha k1, k2, and this single kind of bosonic excitation, this alpha k. So and this is okay. So this G once again is this it's this bare kind of impurity boson interaction. Okay, so but the main point is that actually what you can show is what you can argue. So in the case of an ideal Bose gas, let's go to that situation. In that case, what this alpha k1, k2 is it's just a product of these uncorrelated product of these individual alphas here, alpha k. And so actually, okay, so the way you've written it, what you can show is that actually these two terms then just actually cancel. And so in the ideal case, this function is just zero. And so what you find then is you do indeed recover, this term then is zero here, and I do indeed recover the original, the energy I showed you before, this mean field energy here. Okay, so this term is gone, and I end up with this, and I end up with the associated divergence when A goes to infinity.
Excuse me, just a quick question. Your correlated state, so the variational state, which you call the general correlated state, yes, clearly does not contain the terms of the type B dagger B, which are density variations essentially. So how general is it?
Oh, you're talking about B dagger. Well,
yeah, they're of the same order, and clearly there is no reason not to include those.
Okay. So, but you see, So you're assuming that, so this is, hang on, so are you assuming that you have, okay, so I'm imagining I'm always exciting bosons out of the condensate, right?
Yeah, you have a condensate. Yes, you have a condensate.
Yes.
So it's not a mathematical vacuum. And yeah, if you build a polynomial variational function, which you seem to be doing here, then yeah, probably you should include terms like B dagger B, and not only B dagger. So all those terms are.
But
So
B dagger B, I mean, but the B dagger B, the B will just, well, either it'll just destroy one of these, or it'll just, well, it'll destroy the. I mean,
no. Let's look at the leading order approximation. So the first subleading order. The first subleading order would be alpha naught plus alpha k B dagger K plus beta K BK, because an impurity could potentially dig a correlation hole around it, right? So there's no reason not to add annihilation apparatus to the polynomial expansion. And then you can have all sorts of other terms like B dagger B in the next subleading order BB. So yeah.
But I think, yeah, I don't think that happens if you have if these, okay, so this is the vacuum state for these well, these non-zero B daggers.
Oh, you mean okay? Right. So okay, I see. That is the vacuum state. Okay, so these are the Bogoliubov-Duchenne apparatus. But B dagger B or B dagger are clearly could be added here, and these are non-trivial as far as I'm concerned.
I don't think that changes. I mean, I think this should cover all the possible processes. I mean, I agree that. I mean, you're right that if I had a finite population of like, okay, so this is. We've also looked at, say, finite temperature, and then you're absolutely right.
Okay. Yeah, I got it. I think I understand what's going on.
Yes.
Thank you. Yeah.
But you're right. Yeah.
Sure.
No worries. Okay. All right. Okay. Okay. So basically, right. So if we come back to this correlation one, so we can reproduce the ideal gas. So this function essentially gives some measure of the correlations. Now we have, if I took what's called a coherent state, so that would be basically where I treat, so instead of having ideal Bose gas, now I have Bogoliubov operators, but I still have uncorrelated Bogoliubov operators. So I have an infinite number of Bogoliubov excitations. And what you find actually there is that this function, in this case, is a constant. So and it depends on AB, and really all it is just the mean field interaction that a Bogoliubov excitation, it's mean field interaction with the condensate. So this is at least within that approximation, this function, so this is once again, you think of it as a difference between one boson excitation and two boson excitations. There, the difference is just given by this mean field energy shift for a Bogoliubov excitation. So you see, actually, so in that case, you just have, so that appears to cure the divergence at unitarity, so where A goes to infinity, because now this term is no longer zero. But actually, this divergence just appears is shifted to a positive A. So this just, because now you just have this some kind of constant, or actually negative kind of constant here, which eventually will kind of, once this term matches with that, then it diverges. So you've kind of just shifted the divergence over from unitarity with this kind of coherent state. And finally, okay, so there's another type of approach that people have used, and that's where it sounds rather brutal. It's like what's often called a Chevy type ansatz, where you literally just only keep the lowest order excitation. So you kill all the higher order excitations and just keep this lowest order one, the single boson excitation. And in that case, I mean, okay, you have to go through the maths, but in that case, what you find is, once again, you get a constant for this G, this function. But now it's it's just actually equal to the minus E. Okay, so now you have this sort of implicit equation for the energy that you need to solve. Okay. So So what actually, I mean, okay, so in reality, what you would actually expect is that what we find when we try and do sort of better approximations is that this function should really interpolate between these two types of limits. So in other words, if I take if I'm looking at a situation where the momenta are going to zero, so I'm going to have situations where effectively the bosons become very, we have low, sort of large length scale, low energy physics. The bosons are very far apart. The excitations are very far apart. Then I should recover sort of Bogoliubov type mean field theory. So I should recover this kind of picture here. Whereas now, as I go to very large K, large momenta, so short range, as I bring them closer together, then we encounter this kind of blocking effect I was talking about before, where effectively you're going to suppress these higher order terms, and you should be approaching this kind of physics where you approach this kind of result where you mainly have a single excitation left. Okay. All right, so I'm kind of saying all this stuff. So this is kind of this way you can think about it. Okay, now let me try and show you how we actually sort of argue that or prove that with the calculations. So what we do is we consider two types of approaches. So we have the exact kind of quantum Monte Carlo calculations for the Bose polaron, where we have hard sphere interactions between bosons. And what we also do is we do a kind of a variational kind of approach of this kind of, this sort of ansatz, where we keep sort of a fixed number or finite number of excitations, where we use a slightly different model. What you can think of it as a kind of bosonic Anderson-like model, where instead what we have is now we have a situation where the way the boson interacts with the impurity is it's converted into another channel, like a sort of a so-called two-channel model. So when it interacts, it gets converted into this sort of dimer type state here with some energy here. Okay, so that's kind of this interconversion process here. And the key thing is that so in this case, that only one boson at a time can enter this dimer state. Okay, and so the way you can kind of capture that is if you throw in another term here, this sort of interaction term, if you like, between your dimers here. You take the limit where, so you're sort of taking a hardcore limit. So you take the limit where this interactions between dimers goes to infinity, and that ensures that you can only have one, dimer populated at a time by this bosonic, by the bosons that interact with the impurity. So this sort of is a way of mimicking the quantum blockade effect that I was explaining before, where you can only have one boson at a time interacting with the particle, with the impurity, sorry. Okay, so we take this kind of model, and then, like I said, we use this kind of variational type of approach where we truncate it up to three excitations. And then we compare with the quantum Monte Carlo. Now, this is where this A star parameter, remember this A star is the point at which the trimer unbinds. So the way we're able to compare, so in order to compare, we don't want to compare apples and oranges, we want to compare them on a same equal footing. So what we do is we fix the point at which the dimer disappears. They both disappear in the same, even though we have different models, they both have this feature. So you fix this A star parameter. And this is what we find essentially. So we've plotted the energy as a function of interaction here, and for two different repulsions, as is shown up here, two different, and there's 2 orders of magnitude difference between the two here. And what you can see actually is that the lines are the variational approach and the dots are the quantum Monte Carlo approach, or quantum Monte Carlo calculations. And you can see actually there's quite good agreement between the two approaches, even though they're quite different models. And what this shows really is that at least for these kind of repulsions, that you can capture at least most of the physics just by only including a few excitations, essentially because of this blockade effect. Oops. So what we sort of instead of argue from this is that, what we're seeing is that boson repulsion suppresses many excitations. And moreover, because we're essentially using two models to model this, it seems to be insensitive to the way in which you introduce it to the microscopic details. So we introduce repulsion in one way here, in this model here, and in another way in the QMC. And we see basically the same kind of physics once we fix this A star here. Yeah, so I think, yes, so that's, oh yes, and this dashed line here, this one here is actually the ideal sort of uncorrelated sort of ideal mean field kind of case, which is diverging at this point. Okay, so finally then, so then, okay, so what about if we sat at unitarity? So we sat at the point where the scattering length diverges. Okay, and what you can argue to yourself is that the energy has to take this form. Okay, the polar energy. So it has, okay, so it's just from dimensional analysis. So it has to be some dimensionless function of this AB, this n, well, this gas parameter here, and then the density combination here. Okay, and the point is that we know already that if I take AB to zero, if I take the repulsion to zero, this energy has to diverge, as we've discussed. Like in the ideal case, it's singular. But at the same time, we know that if we took the zero density limit, say for a fixed AB, this energy has to go to zero. Okay, so there's no bound state in this case. There's just zero. So we know that it has to satisfy these two limits. And so what that means is we require this. We know this function. Okay, we know that this function has to go to infinity as this goes to zero. So this x goes to zero, but it has to be slower than 1 over x squared. Okay, to satisfy this property here. And so if we looked at the quantum Monte Carlo, so this is the quantum Monte Carlo data we have at unitarity. What we find is actually it appears to be a logarithmically slow dependence on this repulsion. So quite not a power law at all, actually. So here, this dashed line here is actually what one might predict from a coherent state. So this sort of mean field type of picture, sort of more classical field type of picture. And you can see it drastically sort of overestimates, I guess, the effect or the sort of decrease in energy as you lower this. So really, so we find, yeah, I mean, like I said, I mean, it's so this is quantum Monte Carlo, and I think it's something now, actually, this kind of behavior we cannot even capture within this variational kind of approach, because as you lower the repulsion, you're going to have more and more kind of excitations allowed, as you kind of lower it here. So we cannot really, it's difficult to capture, or we cannot really capture this behavior just with a finite number of excitations. So it seems quite a non-trivial, non-perturbative effect. And it's something that actually would be interesting to look at. So this is for a situation where you have an infinitely massive impurity. We expect a lot of these ideas, well, the quantum blockade kind of effect to carry over to finite mass, but it'd be interesting to see actually how this type of behavior develops, or how much of it survives if we have a finite impurity mass. Okay, so I think I'm running out of time. So I just wanted to say very quickly that just while I mentioned finite mass, that we say basically we observe very similar kind of, we have similar sort of universal kind of quantum blockade behavior, in the sense we can capture like the sort of quantum Monte Carlo behavior just from these sort of very sort of simple kind of variational ansatz with a few excitations. But the main difference is that now you no longer have this logarithmic dependence at unitarity. You have a power law dependence, because you have you have the possibility of FMOF trimers and FMOF bound states, the FMOF effect, which I could spend another talk on. But okay, okay. So then, yeah. So just to conclude, then, so what I've tried to convince you, at least, is that if you if the impurity potential is short-ranged, then you have what I call quantum behavior, in the sense that you have this quantum blockade type of effect that I mentioned, where a boson interaction with impurity will interfere with other bosons interacting with this impurity, at least locally. We have these universal bound states, and we also have this universal logarithmic behavior at unitarity. So what's interesting, yeah, so we expect it to at least to be relevant to cold atoms, at least with heavy impurities, or even equal mass impurities, at least to some, well, certainly heavy impurities. And it'd be interesting to see whether this has any kind of, whether it could be at all of interest to other systems, for instance, photonic systems, you know, where it's of interest certainly to enhance the quantum effect, enhance these quantum type of blockade effects. Okay, so with that, I'll just conclude it. I'd like to acknowledge the people involved, including, well, here's a Zoom group photo here. His our collaborator Jesper Levinson, who will also be soon giving the next talk, and also our other collaborators, Louis Peña-Ardila and Shuei Yoshida. Okay, so thanks for your attention.
Yes, and Xavier. I see your hands. Yeah, first.
No, sorry for the mistake.
I was just clapping.
Sorry, I was clapping. Sorry.
But I can ask a question if you want. This condition, I'm a little bit confused about. I'm sorry, Sue, because we're also taking time from Jesper's talk. So this condition that you have here, that you want the scattering length, what was it, to be the range to be much larger than the scattering length, because otherwise you sort of miss these correlations between the bosons. But what happens if you now do a GP calculation with this impurity potential, and then it predicts a dressing cloud around the impurity, which is very large.
Mm-hmm.
So you stay in the dilute limit of the bosons. So it's like a self-consistent. The classical field assumes that it's dilute and it stays dilute. Why is this wrong then?
I think what I was, okay, so what I was trying to, this is what I was trying to argue with here. So once again, I totally agree that away from the impurity, you can use your classical field approximation. But the point is that once you, if you're trying to just, okay, my point is that the energy of the polaron is very much, affected by, what's happening locally at the impurity. And that is not properly described by the classical field approach, because if you like, the potential is well, okay, maybe another way to think about it is the potential is changing very quickly, or changing on the order of a single kind of boson-boson interaction. So I think that's what I was trying to kind of capture with this requirement here. So you're right, you might have the diluteness condition, but if this kind of fails, this the number of if you only have, like, say, one boson at a time that's interacting in the impurity, it's not really something that can be described by a classical field anymore. Does that make sense?
So
it's not really. I mean, you can't really think of it as
yeah, maybe we can discuss it privately. I'm not sure I completely understand.
Yeah. It's really about, But my understanding is, if whenever people write down, these kind of, people who use Brzezinski, they're always assuming that they have a large enough number of bosons per mode even if say they're describing some spatial dependence. There's always this assumption that you have a large enough number of bosons in any kind of given mode that you can treat it as a classical field. And I'm just saying that breaks down in this case, in this limit. anyway, maybe we can discuss. Yeah. Probably.
Yeah, go ahead. Next question. I saw a couple of hands. Xavier, I saw your hand. You should unmute. Go. Yes.
No, I was just clapping. Okay, no.
Okay.
Yeah, maybe.
It's this one, Michael. This is not raising hand. This is clapping.
I have a question concerning this logarithmic law that you found. First question is that this is for hardcore interaction between the bosons, right? Did you try to increase the range and make it like soft core with the same AB and see if it's stable?
No, we haven't done it. Actually, yeah, that's a good question. I think that's something that well, actually Lewis was doing the QMC, but yeah, that's something that I agree should be looked at. I mean, what I suspect is that okay, obviously we should check, but it may be that it just changes what's the coefficient in the logarithm, but that's of course something we should check.
And the second question is, did you try to wrap some theory around this logarithm? Do I understand?
Yes, very hard. We try. Well, yeah. I mean, because it seemed like tantalizingly, it seemed like something that one should get analytically. But yeah, I mean, we try. Yeah, I couldn't do it. I mean, I guess what was suggestive at least is that we know there are these. Well, okay, we know that this kind of case is sort of singular in many ways, at least in terms of the FMF effect. So we know that there are various exponentials, logarithms that you end up with from the few body point of view in terms of the, like for instance, how the FMF scaling goes with the impurity mass. We know that kind of goes, that has exponential behavior, or if you like so there are kind of these. It looks like these are kind of all floating around. It looks like we should be able to do something with it, but I couldn't actually get it to work from that. But yeah, so I think so the short answer is no, we couldn't get an analytic result, but we tried very hard. So yeah, so if anyone can come up with a possible result for that, I'd be very interested to know about it. Yeah.
Okay, thanks.
May I ask a question?
Yes. Yeah, sure.
Thank you for the interesting talk. I very much enjoyed it. I have a question like regarding this granular nature. And I was thinking, like, according to this limit that you put, it should be actually different in 2D and in 1D. So is it like more like a 3-dimensional effect and then it will be different in 1D, say, just because it's actually in, yeah?
Yeah, I agree. I think 1D would be quite different. I don't know about 2D. 2D might be similar. But yeah, I agree. 1D could be quite different. Yeah. In the sense that then there, at least you can have real repulsive interactions, even when it's zero range, for instance. I mean, you can still have this, repulsive scattering length. Yeah.
Right. I like it's easier to bend, I think, and that's like, and this condition with R0 will be different.
Yeah. So I agree. 1D could be a very different story. Yeah. And yes, I see Nikolai has mentioned the Anderson model has non-interacting bosons in the bulk. Yes, that's right. So it is a very different model, and really what we're demonstrating is actually that at least, okay, so remember we're really focusing on the dilute limit, like very, very weakly interacting limit for a Bose gas. We're finding that at least it's the short range repulsion that seem to matter most, not the kind of long range mean field interactions for the polar energy at least. Okay. All right, probably I should let Jesper start his talk. It's getting getting late, but you can always direct more questions to Jesper. Yes.
Так. Go ahead. Then wait. I should stop. Should stop recording. Так. Oops.